All right, here we are in question 1. The diagram shows the graph of the cubic polynomial f of x. We want to find an expression for f of x in factorized form, where we write each linear factor with its coefficients as integers. Now, in order to do this, we need to know what a root is, and we need to know the definition of the factor theorem. So, what is a root? A root is basically an x-intercept. It is where f of x is equal to 0. Okay, so if we go up here to our graph, where is the polynomial equal to 0? In other words, where is it an x-intercept? Negative a third, 1, and 5 upon 2. So those three things are the roots. Well, then the second thing is, what is the factor theorem? The factor theorem states that if a is a root of f of x, then x minus a will be a factor of f of x. For example, if 2 is a root, x minus 2 is a factor. If 5 is a root, x minus 5 is a factor. And if negative 1 is a root, then x minus minus 1, which is x plus 1, will also be a factor. So what we can do is we can go up and we say our roots are negative a third, 1, and 5 upon 2. So let's go write those down. Right, our roots are x is equal to negative a third, x is equal to positive 1, and x is equal to 5 upon 2. Now, if that's the case, we can write down our factors. Because if negative a third is a factor, then x minus minus a third, x plus a third, if minus a third is a root, then x minus minus a third is a factor, which is the same as x plus a third. If 1 is a root, then x minus 1 is a factor. And if 5 upon 2 is a root, then x minus 5 upon 2 is a factor. Now, what we can do is actually we can convert these factors to get rid of the fractions. If you think about it this way, I could just times this through by 3, and I get 3x plus 1. If I keep this one the same, there's actually no need there. And if I take x minus 5 upon 2 and multiply by 2, I get 2x minus 5. And hopefully it should be fairly obvious to see, right, that if this guy is a factor of the polynomial, then 3 times that guy is also going to be a factor. If this guy's a factor, then 2 times that guy is a factor. Now, the reason I've done this is because in the question, it asks to have integer coefficients. Okay, so that's what I've done there. Now, we can now combine all this and say, since we know our factors, we can write f of x is equal to 3x plus 1 times by x minus 1 times by 2x minus 5. But we need to remember that there is a constant k here. And the reason for that is we don't know if we've got like 3x cubed or 5x cubed or 7x cubed or something. So the constant k is going to tell us that. So how can we find the constant? Well, we've got one other point on our graph that we can observe, which is this point here, the y-intercept. What does that tell us? It tells us that when x is equal to 0, f of x is equal to negative 15. So why don't we just substitute that in? We get negative 15 is equal to k. 3 times by 0 plus 1 is 1. 0 minus 1 is minus 1. And 2 times by 0 is 0 minus 5 is minus 5. So what we're going to end up with here is negative 15 is equal to 5k. And therefore k is equal to negative 3. And if that's the case, we can write f of x is equal to negative 3 bracket 3x plus 1 times by x minus 1 times by 2x minus 5. And that will be our answer. Okay then, part B. I want to write down the values of x such that f of x is less than 0. Well, this is just observing the graph, right? Where is the polynomial going to be less than 0? Well, it's going to be everywhere below the x-axis, right? Because all of these y-coordinates here are 0, and all of these y-coordinates here are 0 too. So the part of the graph that we are looking at is this guy here, isn't it? That guy and that guy. And so we're really asking the question, well, what x values give us that part of the graph? Well, these x values from here to here, and these x values from there onwards. So what's that going to be? Well, this region is x is greater than negative a third, and x is less than 1. And this region is x is greater than 5 upon 2, right? For all of those parts of the graph is below the x-axis, therefore it's negative. And just a special attention, by the way, you were asked to find where the graph is less than, not less than or equal. So therefore, your inequalities here must also not include an equal sign for them to be correct. All right then, question 2, which is a trigonometric graph question. The function g is 5 sine 3/4 x minus 2. And we want to write down the amplitude of g. We want to write down the period of g in degrees. Now, I think this is a helpful place to do some quick recap. If we've got a function where we've got a sine bx plus c, we need to be able to interpret what each of those things means. So typically this is what we call a. This thing here, the 3/4, is what we call b. And that -2 there is what we call c. So we want to define what those things mean. Let's go in reverse order. C is the shift in the y-axis or in the y direction. And that tells you the position of your center line. Okay, so when we sketch it, you'll see what I mean by that in a second. But basically what we're saying is the entire sine graph has been shifted down by 2. Okay, what does B mean, the 3/4? Now, this is where a lot of students get confused because they seem to think it is the period. 3/4 is not the period, but it is related to the period, right? So what this tells us is the number of waves in 360 degrees, or if you're in radians, 2 pi radians, okay? So there are 3/4 of a wave in 360 degrees. Now, that's going to be related to the period. Think about this. If this number wasn't 3/4, let's say it was 2, what that would mean is that there are 2 waves in 360. So how big would one wave be? Well, it would be 360 divided by 2, which is 180. Or another example, let's say that this number here was 3. That would mean there are 3 waves in 360. So how big would each wave be? It would be 360 divided by 3, which would be 120. So how big one wave is what we call the period. And the period, therefore, is equal to 360 degrees divided by that number b. Okay? So in this particular case, our period is equal to 360 degrees divided by 3/4. And if you do that, that would be 120 times by 4, which would be 480 degrees. Okay? So the period of our wave, how big one wave is 480 degrees. Okay, part A, what is going to be the amplitude? Well, as I said, we've got to work through these numbers, right? So the -2 is the shift in the y, the 3/4 is the number of waves in 360. What's this 5 here? What we usually call A, that is the amplitude. And that tells you how much the graph goes up from the center line to the top and down from the center line to the bottom. So in this case, that should be fairly easy. We just say that the amplitude is equal to 5. All right then. Part C then is sketching all of this. So we've got to sketch this on the graph. Well, let's do what I said. Let's go in reverse order. We know that the shift in y is -2. So our graph, I'll just kind of draw it like that, is going to be shifted down by 2, and so that's going to be the center line. What else do we know? We know that the amplitude is 5, right? So the whole graph is going to go up by 5 from the center line. So if I go from -2 up 5, then I'm going to go up to +3. I'll draw that on, so that's kind of like the highest I'm going to go. And I'm going to go down by 5 as well. So -2 minus 5 is -7, right? So my amplitude there is 5 because from the center line, I go up by 5 and I also go down by 5. And then lastly, we got to think about this whole idea of the period. We just said that the period is 480 degrees. That means that one wave takes 480. Well, that's a bit awkward, isn't it? Because we don't have up to 180 on our axis. So we need to think what we can draw. Well, if 480 is one full wave, then 240 is going to be half a wave. And that means 120 is going to be a quarter of a wave, right? So we've got 120, so we know that's going to be a quarter of a wave. So if we're going to draw a sine wave, we're going to start at our center. In the first quarter, we're going to go up to there. And then we're going to start going back down. So we can sort of draw this part of the graph like that. And then you'll be sort of going down, I guess. And on the other side, right, to negative 120, we'll be going down in our first quarter. So that's going to sort of look like that. Sorry, it's not a great graph. Kind of hard to sketch like this, like that. And it's going to go up like that. So I think this is a little bit difficult because unlike many of these questions where you can sketch a whole wave, you can't sketch a whole wave on this one. But you should be able to get the center line, you should be able to get the amplitude, and with a little bit of reasoning about the period, you should be able to draw a graph by, instead of thinking of whole waves, thinking of half a wave or quarter of a wave. Okay, I hope that was helpful. Okay, so here we are in question 3. When ln y plus 2 is plotted against x squared, a straight line graph is obtained. The line passes through these points. We want to find y in terms of x. Okay, well, if we get a straight line, we know that the equation is going to be in this form, y equals mx plus c, right? Because that's the equation of a straight line. And I've used big Y and big X here to distinguish it from our variables little y and little x. But effectively what this means is I can replace that big Y with ln y plus 2 and our big X with that x squared there. So the equation I would get would be ln y plus 2 is equal to m x squared plus c. So this is what this statement here really means, right? If I plot ln y plus 2 against x squared, then, and I know that I get a straight line, it means I can write it in this form here. Now then, the question is effectively, can we find these two constants? Can we find the gradient m? Can we find the y-intercept c? And so the way we're going to do that is we're just going to use our 2 points. So the gradient is y2 minus y1, so 3.92 minus 9.37 over x2 minus x1. So that's 4.75 minus 2.25. Now I'm just going to key that into my calculator. So 3.92 minus 9.37 equals, and then divided through by 4.75 minus 2.25 equals. And that gives me minus 109 upon 50. So minus 109 upon 50. I recommend, by the way, you put that in your calculator 2 times just to make sure. Now, if that's the case, we can actually rewrite this, can't we, as y is equal to minus 109 upon 50x plus c, right? We replace the gradient m with the value we found. And now what we want to do is we want to find c. Well, the way we can do that is we can just substitute in one of our points. So why don't we substitute in this point here? So we can say that when big X is equal to 2.25, we know that big Y is equal to 9.37. So we can write that as 9.37 is equal to negative 109 upon 50 times by 2.25 is plus c. Okay, so I'm just going to put that in my calculator. So minus 109 upon 50 times by 2.25. Okay, and then I'm going to add that then to the other side. So, okay, so plus 9.37. And that's going to give me a y value of 571 upon 40. Okay, or a c value, sorry, of 571 upon 40. So therefore, I can write my equation as capital Y equals minus 109 upon 50, big X, plus 571 upon 40. Well, now, if I want to find my equation Y in terms of X, I just need to replace things. So I need to replace the big Y with ln Y plus 2. And I need to replace the big X with X squared. And then what I can do is I can change everything to exponential form. So I get y plus 2 is equal to e to the power of minus 109 upon 50 x squared plus 571 upon 40. And then I subtract 2 from both sides. So I get y is equal to e to the minus 109 upon 50x squared. And actually, I can split apart that exponential, right? So that's e to the power of 571 upon 40 minus 2. And it really depends what they want for the answer to this, whether they want us to leave things as fractions or to give things as decimals. So I'm just going to check the mark scheme, see what they're willing to accept. So let's say that they accept that the gradient is negative 109 upon 50, so you get a mark for that. They accept the y-intercept as 571 upon 40, right? So they accept that. And what about the final answer? Yeah, they write it as e to the power of 14.3 minus 2.18 x squared minus 2 or equivalent. Well, what I've written is equivalent, right? So the phrase, or rather the symbols OE, when you see that in a mark scheme, it means or equivalent. So what I've written here is equivalent to what you see on the mark scheme. You can change it to decimals if you want, but either should be acceptable. Okay. Okay, question 4, which is a binomial expansion style of question. It is given that the first 4 terms in ascending powers of x in the expansion of this can be rewritten in this form, where n, p, and q are integers. We want to find the value of n, p, and q. Okay, well, what we've got to do is we've just got to expand that using the binomial expansion. So let's have a go at that. We have got 1 minus x upon 2. Now I'm going to rewrite that as plus negative x upon 2, all to the power of n. So then if I expand this, I'm going to get nc0, 1 to the power of n, negative x upon 2 to the power of 0, plus nc1, 1 to the power of n minus 1, negative x upon 2 to the power of 1, plus nc2, 1 to the n minus 2, negative x upon 2 to the power of 2. I've got to keep going for one more term, plus nc3, 1 to the power n minus 3, negative x upon 2 to the power of 3. And of course, it carries on dot, 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 dot. All right, now, before you do anything, what you should do next is you should double check everything. So the powers of 1 should decrease. n minus 1, n minus 2, n minus 3. That looks good. And the powers of the other term should increase. 0, 1, 2, 3. And the same with the NCR term, 0, 1, 2, 3. Okay, so that all looks pretty good. Now what I'm going to do is I'm just going to very slowly simplify all of this. So NC0 is 1. 1 to the power of n is 1. And negative x upon 2 to the power of 0 is 1. Okay, because anything to the power of 0 is 1. Now, NC1 is equal to n. Now, that's something that you should know. If you don't know, just try to do it on your calculator now. Calculate 3C1, it'll give you 3. 4C1 will give you 4. 5C1 will give you 5. So NC1 gives you n. Okay. 1 to the power of n minus 1 is just 1. Negative x upon 2, well, if that will give you negative x upon 2. Next, NC2. Well, you're going to have to use your formula here, and this is given to you in the front of your exam. So let me just go down and write that for you. The formula is that if you've got NCR, right? So the way they write it on the exam is they use kind of that bracket notation, but it means the same thing as NCR. That's equal to n factorial over r factorial times by n minus r factorial. So what I can write here is instead of NC2, I can write n factorial over 2 factorial n minus 2 factorial. And then 1 to the power n minus 2 is just 1. And then negative x upon 2 squared is going to be positive x squared upon 4. And then next term, the NC3, well, same thing, right? That'll be n factorial over 3 factorial times by n minus 3 factorial. And 1 to the power of n minus 3 is just 1. And a negative x upon 2 cubed is negative, right? So I've got a negative times a negative times a negative upon 8, and then plus dot, 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 dot. Okay, now then, I'm just going to get rid of this guy here. Sorry about that. I'm going to simplify again. So I've got 1 times 1 times 1. That is 1. If I multiply out the next term, I'm going to get negative a half nx. If I multiply out the next term, well, the 2 factorial is just 2 times by 4. That's going to give me an 8 on the denominator. So I'm going to write that as an 8th times by n factorial upon n minus 2 factorial. Now I'm going to return to that in a second. And the next term, well, on the bottom, I've got 3 factorial, which is 6. This is 8, so 6 times by 8 is 48. So that will be here negative 1 upon 48 times by n factorial upon n minus 3 factorial times by x cubed plus dot, 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 dot. Now then, we automatically know that these are going to correspond to 1 minus 8x plus px squared plus qx cubed. So in other words, if we just do a little bit of comparison, then this term here, the negative a half n, must be the same thing as the negative 8. This term here must be the same as p, and this term here must be the same as q. So why don't we start by comparing the coefficients of x. So if we compare coefficients of x, I'm going to write that down, coefficients of x, then what we get is negative 8 must be equal to negative a half n. And if that's the case, then n will be equal to 16. Well, okay, then once we know that, sorry, not 16 factorial, beg your pardon, 16. Well, once we know that, then we should be able to get everything else, right? Because we can then compare the coefficient of x squared. So the coefficient of x squared is p, and that will be equal to an 8th times by n factorial, which is 16 factorial, over n minus 2 factorial, which is going to be 14 factorial, okay? And what you could do is you could put that into your calculator, but I just want you to think about that for a second, right? 16 factorial is 16 times 15 times 14 times 13 times 12, all the way to the end. And 14 factorial is 14 times 13 times 12 times 11 times 10. So if you do 16 factorial divided by 14 factorial, all the terms are going to cancel off apart from 16 times 15. So this is actually the same thing as an 8th times by 16 times by 15. Okay, and 16 divided by 8 is 2. So we've got 2 times by 15. That's going to be 30. Right? All right, then lastly, we can compare the x cubed term. And the x cubed term, let's just go to it, was q. And if we compare that with what we got, that is negative 1 upon 48. Negative 1 upon 48 times by n factorial, which is 16 factorial, over n minus 3, which is 13 factorial. And again, using the same principle, 16 factorial times by divided by 13 factorial is just going to leave us with 16 times by 15 times by 14, right? But of course, you could use your calculator if you're really not sure about that. So I'll key into my calculator anyway. So 16 factorial equals divided by 13 factorial is 3360, and I can double check that. 16 times 15 times by 14 gives me the same thing. I'm going to divide that by 48, which gives me 70. So Q is equal to negative 70. So in the end, I think that N is 16, P is 30, and Q is negative 70. And I'm just going to check the mark scheme, make sure I haven't made a mistake. And N is 16, P is 30, Q is negative 70. Yep, exactly right. Okay, then part B of this binomial expansion question. We want to find the term independent of x in the expansion of this thing, giving our answer as a rational number. Now, when it says independent of x, it means that there is no x term. In other words, the x's all cancel off, so what you're left with is a number. Now, the way I would approach this is as follows. You've got 2 upon x squared plus x upon 3 all to the power of 6. And of course, what you could do is you could expand the whole thing, which has got 7 terms, and then find out which term cancels off. But I think there's a more efficient way of doing that. You should know that every single term in this expansion is going to have the following basic form. You are going to have 2 upon x squared to some power times by x upon 3 to some other power, multiplied by a coefficient, which is going to be 6c something, right? So in other words, every single term in this expansion is going to take this basic shape where we've got this term here to some power and this term here to another power multiplied by a coefficient. Now, what do we know? We know that these two powers need to add up to give 6. Okay, so we want to choose two numbers to go here and here that add up to give 6, such that the x's are going to cancel off. So for example, we could choose 0 and 6, 1 and 5, 2 and 4, 3 and 3, and so forth. But one of those combinations is going to cause these guys to cancel off. Well, hopefully what you'll be able to see is that if I was to put a 2 here and a 4 here, then my x's will cancel. Why is that? Well, because this term will become x to the power of 4 on the bottom, and this term will become x to the power of 4 on the top. So what you will end up with is x to the 4 divided by x to the 4, which is going to cancel off everything and just leave you with a constant. So the only other thing we've got to know is what number goes here. Well, it doesn't really matter because we can choose either this guy or that guy. So you can choose 2 or we can choose 4, because 6c2 is the same thing as 6c4. So I'm just going to write that there, 6c2. And now we've just got to simplify this term, basically. So 6c2, let me just put that in my calculator. 6c2 is 15. Okay, if I was to expand this, I would get 4 upon x to the power of 4. If I was to expand the other term, I would get x to the 4 upon 3 to the power of 4, which is 81, right? Because it's 3 squared squared. And therefore, what am I going to have? Well, these guys are going to disappear, dot, dot, like that. And I'm going to have 15 times by 4, which is 60, all divided through by 81. And I think that that should cancel quite nicely, but I can just use my calculator to give 20 upon 27. So we want to leave our answer as a rational number. And the rational number is 20 upon 27. And maybe you want to write something like, is the term independent of x? Just to be totally sure. Okay. Okay, here we are in question 5, which is a trigonometric question. We want to solve 3 sec squared bracket 2 theta plus pi by 6 is equal to 4 between this slightly unusual domain of negative pi by 2 and positive pi by 2, giving our answers in terms of pi. Okay, well, the first thing I would do is I would use a substitution. I would say let u equal 2 theta plus pi by 6, right? So I think that that's going to make our problem a little bit easier later on, especially. And that means that if I was to rearrange that, theta would be equal to u minus pi by 6, all divided through by 2. Now, that means that I can change both my equation here and also the domain here, so I get it in terms of u. So let's just do that. I'm solving 3 sec squared u is equal to 4. And my domain is between negative pi by 2 and positive pi by 2. But now I'm now going to replace that theta with u minus pi by 6 all upon 2. And so what I'm going to do is I'm going to multiply both sides by 2. So that's going to be minus pi. And pi are the set of boundaries for u minus pi by 6, right? And then what I'm going to do is I'm going to add pi by 6 to everything. So negative pi plus pi by 6 is minus 5 pi by 6. And pi plus pi by 6 is 7 pi by 6. So actually what we're trying to do is we're now trying to solve this equation within this domain. So we've converted the problem from a problem with theta to a problem with u. Now, we're going to try to make this a bit better as well. So sec squared u is equal to 4 upon 3. And hopefully we should know that sec is the same thing as 1 divided by cos. So cos squared u will be equal to 3 upon 4, right? So if I just flip it. Now, if you're not sure about sec, cosec, and cot, by the way, the best thing is always to think about the third letter. 1, 2, 3, c. So sec is 1 divided by cos. If you had cosec, right, the third letter is s, so it's 1 upon sine. And if you have cot, the third letter is t, so it's 1 upon tan. So that's that. And then lastly, we need to square root this. So cos u will be equal to plus or minus the root of 3 upon 2. Okay, now I think the plus and minus there is something that a lot of people are going to forget, which means you're going to lose out solutions. So the key thing I'm trying to get to you is we are using a substitution so that now what we are doing is we are solving this equation with this domain in terms of u instead of this one, which I think is a bit harder. Okay. All right, then, how are we going to do this? Well, we could use quadrant method and the unit circle and all of that. I'm going to use a graph for this one, if you don't mind. You know, it's good to know 2 or 3 ways of doing these type of questions. So what are we going to do here? If we want to find where cos u is equal to plus root 3 upon 2, well, that's the same thing as trying to find where the graph of cos x intersects with y is equal to root 3 upon 2. So if I was to draw y is equal to root 3 upon 2, let's say it's something like that. Yeah. So y is equal to root 3 upon 2. What we're really looking for is we're looking for the intersections, okay, which would be there, 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 and there. Okay, now, if we use our calculator, we will get our first intersection, and our first intersection will be pi by 6, right? So cos inverse of root 3 upon 2 is pi by 6. Well, this means that by reflection, this point must be negative pi by 6, right? Because this point and this point are reflections in the in the y-axis. Now, the next thing is to understand that the sine wave and the cosine wave, they repeat each other and they have a period of 2 pi. What that means is that one whole wave takes 2 pi radians. So if I was to start at this point here and move another 2 pi, I'm going to get to the next intersection point here, right? So this guy is going to be equal to pi by 6 plus 2 pi radians. Okay, so pi by 6 plus 2 pi is going to be, what's that? 2 pi is 12 pi upon 6. That's 13 pi upon 6. Yep. And same with this guy, right? How do I find this guy? Well, that's the same thing as this, negative pi by 6, but I move another wave to the right. So I'm adding 2 pi. So I've got minus pi by 6 plus 2 pi, which is 11 pi upon 6. Now, the important thing to notice, just write that a bit neater, because it's a bit slightly rubbish there. 11 pi upon 6 is that both those solutions we don't want because they're greater than 7 pi upon 6. So we're not interested in those, so I'm just going to cross them out. Gone. But we may be interested in these guys over here, right? So this guy is going to be pi by 6, but minus 2 pi. And so if I subtract 2 pi there, I'm going to get minus 11 pi upon 6. And again, we're just going to compare it with our domain. Negative 11 pi upon 6 is further than negative 5 pi upon 6. So again, we're not interested in that guy. That guy's gone. Okay. All right. So we got our solutions for the intersection of plus root 3 upon 2. Now, what about minus root 3 upon 2? Well, we just have to draw another line of intersection, right? So that would be where y is equal to minus root 3 upon 2. And so what are the intersections we want here? Well, we're going to get this intersection and this intersection, this intersection and this intersection, and so on and so forth. And I'm going to use my calculator. So I'm going to type minus root 3 upon 2. I'm going to do the cos inverse of that. And what do I get? I get 5 pi upon 6, right? And that should actually make sense, right? Because this distance here is pi by 6, and by symmetry, that distance there must also be pi by 6. So this coordinate is going to be pi minus pi by 6. That guy there is 5 pi by 6. And by symmetry, this guy is going to be minus 5 pi upon 6. Okay? And then that's already at the limit, right? Because negative 5 pi upon 6 is the lowest we can go. In fact, this guy is not even included, is it? Because it's less than, we've got to be greater than negative 5 pi upon 6, not greater than or equal to. So even this guy is out, so we're not interested in him. Then what we've got to do is we've got to find this guy. Well, this guy is the same as this coordinate here, but just plus 2 pi. So we've got negative 5 pi upon 6 plus 2 pi, which is 7 pi upon 6. This guy here is 7 pi upon 6. And again, we want to be less than 7 pi upon 6, not less than or equal to, so that guy no longer is valid. So we have got 3 solutions. We have got that u is equal to either negative pi by 6 or pi by 6 or 5 pi by 6. But now what we want to do is want to convert that to solutions for theta. And theta is u minus pi by 6 upon 2. So theta is equal to u minus pi by 6, then all divided through by 2. Well, what we've got to do then is just got to take our values, subtract pi by 6, and divide by 2. So if I take this guy, subtract pi by 6, I get minus 2 pi upon 6. And I divide by 2, I'm going to get minus pi by 6. This guy, if I subtract pi by 6, I get 0. And if I divide by 2, I get 0. And if I've got 5 pi upon 6, and I subtract pi upon 6, I get 4 pi upon 6. And I divide by 2, I'm going to get 2 pi upon 6. Yeah, and 2 pi upon 6 is the same thing as pi by 3. So I'll probably just change that to pi by 3. Okay. All right, now that's quite a long and complicated question. So I'm just going to check my answers against the mark scheme, make sure that I have got that right. Yeah, negative pi by 6 is 0, and pi by 3 or equivalent answers. But remember, you need to leave your answers in terms of pi. I think that is extremely difficult, guys. I must say, I think that's quite a hard question so early on in the paper. But I hope my explanation is clear. And I really would just recommend using substitutions here and applying that substitution to the domain, because that will help you to understand what set of values you require for your solution. It's very easy to miss out solutions if you're not being careful. Okay, question 6, which is a factor theorem, remainder theorem question. Actually, we've kind of got another one in this paper. The polynomial p of x is given that p of x is ax cubed plus bx squared plus cx minus 5, where a, b, and c are integers. It is given that p prime of 0 is equal to 12. It is also given that p of x has a factor of 3x minus 1 and a remainder of 95 when divided by x minus 2. Well, basically, we've got 3 bits of information there, right? This bit of information, this bit about the factor, and this bit about the remainder. And we just got to use these 3 to find a, b, and c. So why don't we start with the first one? P prime of 0 is 12. So what I got to do is just got to differentiate my function. So if I differentiate p prime x, I'll get 3ax squared plus 2bx plus c. And then what I'm going to do is I'm going to substitute in 0 into that, which gives me 3a times by 0 plus 2b times by 0 plus c. So that's going to be equal to c. And we're told that p prime of 0 is equal to 12. Therefore, c is equal to 12. Okay, so that should be relatively straightforward. The next part, we are told that p of x has a factor of 3x minus 1. Now, in I think it's the first question in this paper, I explained what the factor theorem was. Basically, the factor theorem states that if x equals a is a root of f of x, then x minus a is a factor of f of x. Okay, that's the key idea. So if 2 is a root, x minus 2 is a factor. If 5 is a root, x minus 5 is a factor, and vice versa. If x minus 7 is a factor, then 7 is a root. And if x minus 10 is a factor, then 10 is a root. Now, in this particular question, we've got 3x minus 1 is a factor. Well, what does that mean? That means that x is equal to a third is a root. Now, I know that seems a little bit different to what I just said, but it's only a very slight difference. What we're going to do is we're going to set our 3x minus 1 equal to 0. And if we rearrange that, we get x is equal to a third. What's the principle going on here? Basically, what we're saying by this statement is that if we were to substitute the root a into here, then the factor is going to become 0. And if the factor becomes 0, then that's the same thing as having a root. So in this particular situation where we've got 3x minus 1, if I was to substitute a third into this factor, the factor becomes 0, and therefore the whole polynomial becomes 0, which is the same thing as having a root. Okay. Anyway, this means that I've got to substitute a third into my polynomial. So just to restate, polynomial, what was it? P of x is ax cubed. So P of x is equal to ax cubed plus bx squared plus cx, which was 12, so plus 12x minus 5. And now what we're saying is that p of a third must be equal to 0, because if a third is a root, then the definition of a root is if I substitute it into the polynomial, I will get 0. So this is going to be a times by a third cubed, which is 1 upon 27, plus b times by a third squared, which is 1 upon 9, plus 12 times by a third, which is 4, minus 5 must be equal to 0. Well, I think it's probably better for us to get rid of the fraction. So I'm going to multiply everything through by 27. So that will be a plus 3b. 4 minus 5 is -1. So -1 times by 27 is -27 is equal to 0. But it's probably better for us to write that as a plus 3b is equal to positive 27. And that will be an equation that we will be able to use later. Last statement. The last statement is that we have a remainder of 95 when we divide by x minus 2. Well, what does that mean? It means that if I was to substitute 2 into the polynomial, I would get 95. Okay, so that's the remainder theorem. The remainder theorem here states that if I was to substitute, what was it? Was it 2? Yeah, 2 into the polynomial, then I would get 95. So let's just do all of that. So we're going to get a times by 2 cubed, which is 8, plus b times by 2 squared, which is 4, plus 12 times by 2, which is 24, minus 5 is equal to 95. So therefore, 8a plus 4b is equal to, well, if I add 5 to both sides, I'm going to get 100. Then 100 minus 24 is 76. And I think it's probably going to make a lot of sense to divide everything through by 4. So that'll be 2a plus b is equal to 76 divided by 4. I'm just going to do that on the calculator because I don't trust my brain. And so that's going to be my second equation. Well, what have we got here? We've got 2 equations and 2 unknowns. And how do you do 2 equations and 2 unknowns? Well, simultaneous equations. So I'm going to write these guys out. A plus 3b is equal to 27. And 2a plus b is equal to 19. And I think, generally speaking, the best way to do these is by using elimination. So I'm going to double the first equation. So I get 2a plus 6b is equal to 54. And keep the second equation the same. 2a plus b is equal to 19. And then subtract, right? So 2a minus 2a is 0. 6b minus b is 5b. And 54 minus 19, again, I'm so sorry. I'm just quite tired today. I'm just going to do that, is 35. Therefore, b is equal to 7. And if b is equal to 7, then we can just substitute in. So we'll substitute into the first equation. A plus 3 times by 7 is 21 is equal to 27. Therefore, A is equal to 6. Okay, so A is 6, B is 7, and our C was 12. So let me just go to the mark scheme, check that that is all right. Yep, that's all correct. Okay, so here we are in part B. We now want to show that the equation p of x equals 0 has only one real root. So I'm going to write the polynomial out, but now with our values of a, which is 6, b is 7, and c is 12. And hopefully what you remember was that a factor was 3x minus 1. I think I was right if I just go back. Yeah, 3x minus 1 was a factor. And so therefore, we should be able to divide this entire polynomial by 3x minus 1. So that's what I'm going to do. I'm going to take this guy, 6x cubed plus 7x squared plus 12x minus 5. I'm going to divide it by 3x minus 1. So let me just do that. Okay, now how do we do polynomial division? Well, this guy here, the 6x cubed, is our leading term. And so we take the leading term, we divide it by 3x. If we do that, what we will get is 2x squared. We then take that 2x squared and multiply it by everything here in the divisor, which is going to give us 6x cubed minus 2x squared. And then what we do is we are going to subtract the bottom from the top. So 6x cubed minus 6x cubed, right? This minus this is 0. 7x squared minus 2x squared is 9x squared. And we've still got our 12x minus 5. Now then, 9x squared is our new leading term. So we're going to divide that by 3x. If I divide 9x squared by 3x, I get plus 3x. I then take that 3x and multiply by everything in the divisor, which gives me 9x squared minus 3x. Again, what I'm going to do is I'm going to subtract off. So 9x squared minus 9x squared, that thing is 0. 12x minus 3x is 15x minus 5. 15x becomes our new leading term. We're going to divide that by 3x, and that's going to give us plus 5. And if I multiply 5 by 3x minus 1, I get 15x minus 5. Which if I subtract off gives me 0. So I've got no remainder. So I've confirmed again that 3x minus 1 is a factor. Well, this means that I can then rewrite our polynomial p of x as equal to 3x minus 1 times by this quadratic factor, 2x squared plus 3x plus 5. 2x squared plus 3x plus 5. Now, what does the question ask? The question says we want to show that it's only got one real root. Well, if it's got only one real root, then it means that this quadratic factor does not have any real roots. And that means that the discriminant, the b squared minus 4ac, would need to be negative. So let's just check our b squared minus 4ac. b squared minus 4ac. So our b is 3, so we get 3 squared minus 4. So that's b minus 4a. A is 2. And our c is 5. So if I was to multiply all this, I got 9 minus 4 times by 5 is 20, times by 2 is minus 40. And actually, we don't really care what that value is. It's negative 31. But the key thing is this is negative, right? That is a negative number. And so we can conclude with a statement that says, since the discriminant is negative, the quadratic factor has no real roots, and therefore f of x, or p of x, sorry, therefore p of x only has one real root. Okay, there you go. And that is our answer. Okay, this is question 7, which is a permutations combination style question. A 6-digit number is to be formed using the digits 0 to 9. Each digit can be used only once in any 6-digit number. A 6-digit number cannot start with a 0. Find how many 6-digit numbers can be formed. And part 2, find how many of these are divisible by 5. Now, at the start of all these questions, I always recap the difference between permutations and combinations, because this is the biggest error that students make. You cannot decide very often whether to use NPR or NCR. So let's try to figure out what the difference is between them. Permutations, NPR, represents the number of ways to arrange R items taken from N items, right? So if we said 5P3, what we mean is that's the number of ways to arrange 3 items taken from 5. Whereas NCR is the number of ways to choose R items taken from N. So 5C3 would be the number of ways to choose 3 items taken from 5. Now, the difference is with these words, arrange and choose. And the basic distinction is, if we are arranging something, the order matters. If we are choosing, the order doesn't matter. So, for example, the classic example is if I'm forming a code, right, like a password, the order of the letters is important, right? It's not just that I have the right letters, I need to have the letters in the right order. So the arrangements are important, so we would use permutations. But if I'm selecting people to form a football team or whatever, or some other thing, and the order doesn't matter, right? I just want to choose 5 people out of 8, then we would choose combinations, because what we're saying is it doesn't matter if I choose John, Paul, George, and Ringo, or George, Ringo, Paul, and John, or Ringo, Paul, John, and George, right? It doesn't matter the order in which I choose them. So long as I've got those people, then it's all the same thing. Okay, so in this question, 7a, we need to try to figure out from the context whether order matters. And we are creating a number, aren't we? Right? That's the whole thing. We're creating a 6-digit number. So if I was to have the 6-digit number, for example, 1, 2, 3, 4, 5, 6, right? That's a 6-digit number. And I was to take those 6 digits and rearrange them to 4, 3, 2, 1, 6, 5, right? The digits for this number are exactly the same as the digits for this number, but the point is these are 2 different numbers, right? Because the arrangement, the order of the digits is important. It makes this thing into a different number. So what I'm going to do is we got to use permutations. All right, so now let's dig into the question. How many 6-digit numbers can be formed? Well, let's draw it out. 1, 2, 3, 4, 5, 6. Right now, for the first digit, we can't have 0. We can only have the digits 1 to 9. So there are 9 ways of choosing the first digit, right? 9 ways of choosing the first digit. However, for the remaining digits, there are no restrictions at all. So what have we got? Well, we have got to arrange 5 digits there taken from 9 digits. Now, why is it 9 digits? Well, because originally we had 10, but we've already used one for the first digit. So what we've got is we've got 9 digits to choose from, and we are selecting 5. And so therefore this is 9P5, because what we're saying is we are arranging 5 taken from 9, the order matters. Now, the second thing about this is we've got to multiply these guys. We've got to do 9 times by 9P5. Now, why are we multiplying? The basic distinction is between the word and or, right? If we want this and this at the same time, then we need to multiply. If we've got this or this, then we need to add. That's kind of a rough rule of thumb. And what I'm saying is here is we need to have the first digit and the remaining 5 digits, right? We've got to have both at the same time, and therefore we are going to multiply. Okay, so let me do 9P5. I'm going to multiply that by 9. I get 136,080. So I'm just write it down. 136,080. Okay, so that is that's part 1. Okay, part 2. How many of these 6-digit numbers are divisible by 5? Well, we just got to do the same thing, right? 1, 2, 3, 4, 5, 6. And what we're saying is the first digit can be anything from 1 to 9. It just can't be 0. Well, now we've also got a restriction for the last digit, right? What's the last digit got to be? If it's divisible by 5, this guy can only be 0 or 5. Okay? Now, there's a bit of a complication here, and the complication is that the digit 5 can either be at the end or it can be at the beginning. And so the way I prefer to handle this is to think about two different cases, right? I'm going to think about the two cases where the last digit is 0 and also where the last digit is 5. So let me try to explain what I mean. So I'm going to write this down. If the last digit is 0, right? If the last digit is 0, then how many ways can I choose that last digit? Well, there's only one way, right? Only one way I can choose 0 is I choose 0. That's one way. Well, then how many ways can I choose the first digit? Well, I can only choose the digits 1 to 9 anyway, right? So I've still got 9 choices, right? So that's 1 times by 9. And then what I've got is I've got the remaining 4 digits, okay? All right, then. I originally had 10 digits to choose from. I've chosen 2, which is the first and the last. So I've now got 8 digits remaining. And I want to have 4. And the order matters. So this is going to be 8P4, right? So let me just recap. There's one way of choosing that last digit and 9 ways of choosing the first digit and 8P4 ways of choosing the middle digits. So I multiply. However, we've got another case to consider, right? It could be, or the alternative is that the last digit is 5. And if the last digit is 5, how many ways could I choose the last digit? There's one way. Now, how many ways could I choose the first digit? Well, I can have the digits 1 to 9 apart from the digit 5 because I've already used that. So actually this time what I've got is I've got 8 choices for the first digit. And for the middle, well, I've had 10 digits, I've used 2, so I've got 8 remaining, and I'm choosing 4. Order matters, so that's 8P4. Okay, now the key thing is about this is that we have got either this case or this case. If you remember what I said a moment ago, when we've got and, we multiply. When we've got or, we add. So what we're going to do here is we're going to add up these guys. We've got 9 lots of 8P4 plus 8 lots of 8P4. So that's going to be 17 lots of 8P4. If I just put that into my calculator, so 8P4 equals times by 17, I'm going to get 28,560. 28,560. Okay. Now, guys, on the mark scheme, I'm sure there are usually quite a few ways of doing this type of question. But I like this way of cycling through the various alternatives. I think that is a relatively, it's a method that should be easily repeatable in different contexts. So I advise you, if you've understood what I've done and you're happy with that, then learn how to do that. See if you can apply it to other similar questions on past papers. I think it would be a kind of helpful thing for you to do. All right. Okay, then. So part B of the permutations combinations question. A committee of 7 people is to be chosen from 6 doctors, 10 nurses, 8 dentists. Find the number of different committees that can be chosen. Now, at the start of this question, so for part A, I defined the distinction between permutations and combinations. And basically the distinction is for permutations, order matters. For combinations, order doesn't matter, right? We're just choosing people. We're not arranging them. So in this context, again, we need to ask the question, does order matter or not? And we're just forming a committee, right, of people. It doesn't matter the order in which I choose the people. So long as I've got the same group, then everything should be fine, right? So if I choose a group of 4 people and it's John, Paul, George, and Ringo, it's the same thing as choosing George, Ringo, Paul, and John, right? Exactly the same thing. Now, how many committees can be chosen? Well, if there are no restrictions, how many people have I got to choose from? I've got 6 plus 10 plus 8, which is 24, isn't it? Oh my goodness, I'm very sleepy today, guys. So 6 plus 10 plus 8. Oh my goodness, yeah, 24. And I'm choosing 7. So that is going to be 24C, C7. So what I'm going to do is I'm going to put that into my calculator. 24 C7 is 346104. So 346104, right? So that should be that. Okay, now part 2, find the number of different committees that can be chosen if all the doctors have to be on the committee. Well, if all the doctors have got to be on the committee, right, then there are going to be 6 doctors on the committee. Then all we're really doing is we're just choosing one remaining person because we've got to have 7 people on the committee. So how many people have I got left? I've got 18 people left, and I've got to choose one. So that's going to be the same thing as 18C1. But if you just think about it, that's got to be equal to 18, right? If I've got a committee of 7 people, I've already chosen 6, I've got 1 person left remaining, and I've got 18 people to choose from. How many ways can I do it? Well, it's 18, right? Because I either choose one of the 18 people. Okay, so hopefully that should also be make intuitive sense. All right, now part 3, find the number of committees that can be chosen if there has to be at least 1 dentist on the committee. Now, I think the easiest way to do this is to say we could cycle through all the alternatives where there is 1 dentist, or 2 dentists, or 3 dentists, or 4 dentists, or 5 dentists, or 6 dentists, or even 7 dentists. But that's going to be very tedious. It's going to take us a lot of time. And hopefully you should notice there's only 2 marks here. So the better thing to do is to calculate the one alternative that we can't have, which is where we have no dentists, right? So if we have no dentists, then how many ways can we fill the committee? Well, we've got 6 doctors and 10 nurses. That's 16 people, and we're choosing 7 of them. So that would be 16C7. So the number of ways with no dentists is 16C7, which is 11,440. Okay. And earlier on in the question in part 1, we said the total number of committees that can be chosen is this guy here, 346104. 346104. So if this is the total number of committees, and this is the number of committees with no dentists, then if we do 346104 minus 11,440, then what we're going to be left with is the number of committees where there is at least 1 dentist. So if I do that, the answer I get is 334664. And what I'm going to do is just going to go check my answers against the mark scheme. Just make sure that I am right. Let's go down. Yep, that's right. So easier in this case to think about the one alternative you cannot have instead of cycling through all the alternatives that you could have. Okay, here we are in question 8, which is a function style of question. And in general, my experience has been that a lot of students have found these questions to be extremely tricky, often because they're more conceptual questions or they involve explaining ideas. So before I do this specific question, what I'm going to do is I'm going to try to explain the basic principles. That is, I'm going to explain one-to-one, one-to-many, and many-to-one mappings. And I'm going to try to explain the idea of an inverse function. And then hopefully the answers to this question are going to make sense. So first of all, let's talk about the idea of mappings. I've done a longer video by the way, on my channel. If you would want to look at that, you may find that helpful. But I'll try to recap it very briefly. Imagine we've got a function like this, which is just a straight line. Okay. Now, this is an example of a one-to-one mapping. Now, why is it a one-to-one mapping? Because if I imagine I've got one input here, that maps onto one output and only one output, right? And vice versa, right? If I've got an output, that was caused by one and only one input, right? So the words here, right, one-to-one is referring to inputs to outputs. So in this particular case, one input corresponds to one and only one output, okay? Now that's going to contrast with a many-to-one. So if I was to draw a many-to-one function, the classic example of that would be the quadratic y is equal to x squared. So let me try to draw that. Here's a quadratic. Sorry about the rough curve like that. Okay, so let's say that's y is equal to x squared. This is an example of many-to-one. Why is that? Let's imagine that we've got an input 2. If we square that, the output is going to be 4. But similarly, what we could have done is we could have chosen the value -2, and that would also give us the same output of 4. So can you see what's happened here, right? We have got many inputs, or in this case, 2 inputs, that would give us the same output, which would be 4, right? So 2 inputs give us 1 output. So this is a many to 1 mapping, okay? All right then, let's do the last one. Let's do a 1 to many mapping. Sorry about that, beg your pardon. 1 to many mapping, we could do the graph of plus or minus the square root of x. So I'll draw that to look like this. Okay, sorry about that. So that's y is equal to plus or minus the square root of x. This is an example of a 1 to many. Okay. And why is that? Well, let's say we chose the value 9 as our input. That would have an output of positive 3. But similarly, it would also have an output of negative 3, right? So in this particular case, we've got the situation where we have one input, 9, has 2 alternative outputs. So this is one input to many possible outputs. Now, the key thing for you to understand about this is absolutely essential, is that this is not a function. That's the key thing, right? So 1 to many is not a function. Let me try to spell function properly. And I think probably the easiest way to explain this is to think about a computer. In a computer, what you've got is you've got lots of different functions feeding into each other, right? So let's say we've got a function f, and the output of f is going to go into g, and the output of g is going to go into h, right? So we can imagine this is how sort of computer programs work, right? I put in an input, and that input goes into function x, a function f, then the output of f goes into the function g, and the output of g goes into h, and then we get our final output at the end. Now, let's imagine that f was actually 1 to many. Then what's going to happen there is we're going to get 2 possible outputs. We could get this guy, or we could get this guy. Now, for a computer, that is a massive problem. The reason is that a computer cannot decide which of these outputs it should give, and therefore which one should go into the next function g. Computers don't make decisions, right? They just do what we tell them to do. So if we put an input into this function and it says, oh, the output could be positive 3, but it could also be negative 3, then we're going to end up with a problem, right? We need to decide which one is the one output, okay? All right, so that's the key idea. Now, following on from that is the concept about inverse functions, right? What does an inverse function do? An inverse function is like this. Let's say I've got a function f, right? I put in inputs x and I get outputs y. What is the job of the inverse function? The inverse function is to take those outputs y and to give me back my original input x, right? So that the whole job of the inverse function is it reverses the original function, so it takes me from my output back to my input. So just to put some numbers on it, right? Let's say the original input was 2 and I got an output of 5. And that means that for my inverse function, if I was to put in 5, I should get out 2, okay? Now then, let's try to apply what that means to these mappings. If I've got a 1-to-1 mapping, right, and I invert it, then I'm switching my input and output, right? So I switch my input and my output. So 1-to-1 would reverse to become 1-to-1. So that's okay. But now let's look at this guy. If we've got a many-to-1 mapping and we switch the inputs and outputs, then suddenly we have got 1 to many, right? I switch many to 1, I've got 1 to many. So that would become 1 to many. Now, what's the problem with 1 to many? Right, so this is if I try to invert it, what's the problem with 1 to many? This guy is not a function. Not a function. That's the key thing, okay? And because that's not a function, we cannot invert a many to 1, right? So that's the big idea. If we've got a function which is many to 1, we know that it cannot be inverted, because if it's inverted, it becomes 1 to many, and 1 to many is by definition not a function. Therefore, what we need to do is we need to take this mapping here and we need to cut it in such a way that it becomes 1-to-1, right? So we no longer want it to be many-to-one, we want it to be 1-to-1. So for example, we could take like that part of our curve, or we could take that part, or we could take this part. But what we can't do is we can't take like that part there, because that would still be many-to-one. So we need to cut our curve in such a way that we can guarantee it's 1-to-1. And generally speaking, in these questions, what you're going to do is you're either going to choose the whole right-hand side of the curve, or you're going to choose the whole left-hand side of the curve. Okay, that's going to be the idea. All right, so now let's go to our question. Let's have a look at this guy here, 8a. It is given that f of x is equal to 3x plus 1 squared minus 4 for x is greater than or equal to a, and that f inverse exists. We want to find the least possible value of a. Well, basically, what I would suggest you do is you just try to draw the graph, right? I think that's a helpful thing, and you're going to have to do it in the end anyway, because that's like the last part of this question. So I'm going to draw this, that, like that, and let's say that's 1, 2, 3, 4, 1, 2, 3, 4. Sorry about that, and 1, 2, 3, 4. 1, 2, 3, and 4. Okay. Now, what is the graph going to look like? It's a quadratic graph. The minimum is going to be x is equal to negative a third, and y is equal to negative 4. So x is equal to negative a third. It's going to be like here. So negative a third. And y is equal to negative 4. So I've got to extend my line a little bit. Just sort of extend it down. Negative 4. And so my quadratic would kind of be going through there. Now, if you're a little bit unsure about that, right, basically what I'm doing there is I'm finding the coordinate of the vertex. How do I find the coordinate of the vertex? I set this term equal to 0, right? So I say 3x plus 1 is equal to 0, so x is equal to negative a third. That gives me the x coordinate of the vertex, and the y coordinate is going to be this thing here, negative 4. So that's how I've got that. So if I was to draw this quadratic, and I should probably also indicate where it crosses the y-axis, right? Crosses the y-axis when x is 0. If x is 0, I'm going to get 1 squared, which is 1, minus 4 is negative 3. I could also say that I know that my graph is going to cut through here, isn't it? So if I was to draw this, I'm going to get, oh, this is going to be horrible. I'm so sorry. This is not a nice graph. It's not easy to draw graphs on the thing. It's going to look something like that. Okay. I won't draw it all the way. Now, the point is this. We want to find the least possible value of a. So we want to find this domain such that f inverse exists. Well, what I said earlier is that in order for this mapping to be invertible, we need it to be 1-to-1. So if it's going to be 1-to-1, we've got to cut it in such a way that we've got either the right-hand side or the left-hand side. And in this particular question, what we're going to be doing is we're going to be taking values that are greater than or equal to a. So that basically means we're taking the right-hand side of this graph. Okay, so what I'm going to do is I'm going to erase that bit there, right? We're saying we're taking that part of the graph, and that makes it a 1-to-1. So we require that the domain is x is greater than or equal to negative a third, which is the same thing as saying a must be equal to negative a third. Okay. All right, using this value of a, write down the range of f. Well, it's a quadratic that goes on forever and ever, right? So it's always going up, but the minimum value is here, which is at negative 4, right? That represents the lowest value of y, but beyond that, the graph keeps on going up and up and up and up and up. So what's our range? Our range would be everything that's greater than negative 4. So we can say f must be greater than or equal to negative 4, right? Domain is all the inputs, it's all the x values. Range is all the outputs, all the y's. Okay. Now using this value of a, sketch the graphs of y equals f of x and f inverse of x on the axis, stating the intercepts with the coordinate axis. Well, I'm probably going to want to find the x-intercept of f, I think. So I'm just going to do that quickly. So where's the x-intercept? x-intercept is when y is equal to 0. So I can do that by writing 3x plus 1 squared is equal to 4, right? Just rearranging, which means that 3x plus 1 is equal to plus or minus 2. We're just really interested in the positive one for this case. So we say that 3x is equal to 1. And so x is equal to a third, positive a third. So we know that the x-intercept there must be positive a third. So what I'm going to do is I'm just going to change my graph a little bit. Try to get it all through there. Let's try to get it up. It's not going to look very nice, guys. I'm sorry about that. I hope that you can do better because you'll have not trying to use a tablet. Sorry. Okay, so that's kind of roughly what y equals f of x looks like. Now, what will f inverse look like? Well, f inverse is a reflection in the line y equals x. So a good thing for you to do is to draw the line y equals x. I'm going to try to draw it like that. Right, that's line y equals x. And if it's a reflection, what it means is that all the coordinates get reflected around that point. So for example, this coordinate here, right, the vertex point where x is negative a third and y is negative 4, that becomes flipped. So the x coordinate is negative 4 and the y coordinate is negative a third. Okay, so this guy here, we want to have negative 4 and negative a third. Okay, that's going to be the vertex point. And similarly, this x-intercept here at positive a third is going to become the y-intercept of positive a third. And then it should intersect through at that point there. So now if I draw this, oh, by the way, one other thing. This coordinate here we said earlier was negative 3, right? That's the y-intercept of the graph. So if that's reflected, that's going to become an x-intercept at negative 3 as well. Right, so there we go. We labeled all those points on. So now all I've got to do is just got to connect up the dots. And that's, again, I'm sorry, that's going to look a little bit ugly. Oh dear. Something like that. Okay. Okay, now one other thing, by the way, I think is helpful to know is I said earlier that the whole point of an inverse function is that the inputs and the outputs, they flip. So another thing you can think about is the domain and range, right? So domain and range. And domain is all of the input values, right? So the domain of the original function we said was x is greater than or equal to negative a third. And the range is all the output values. So that's y is greater than or equal to negative 4. Well, if an inverse function switches the inputs and the outputs, right? If it inverts them, then what's going to happen is the set of all the inputs for the original function is going to become the set of all the outputs for the inverse function, right? So the domain becomes the range. So the range of the inverse function is going to be y is greater than or equal to negative a third. And similarly, right, all of the outputs for the original function is going to become all of the inputs for the inverse function. So the domain for the inverse function is going to be x is greater than or equal to negative 4 because that's the same as the range of the inverse function. So now what I can do is I can look at my graph and go, my inverse function, is the domain everything that's greater than negative 4? Is it this thing? Yes, it is, right? Because it's negative 4 there, everything to the right. And is my range everything that's greater than negative a third? Well, here's negative a third, right? And yes, it goes up like that. So that's a way of kind of making sure that all the pieces fit together. So we understood how it is that we've reached this graph here. Okay, guys, so I think it's quite tough, but try to make sure you understand the idea of mappings, one-to-one, many-to-one, one-to-many. Why a one-to-many is not a function, and therefore why a many-to-one mapping cannot be inverted. And then see if you can also understand these ideas of domain and range. I think if you can kind of get a grip on that conceptually, these questions go from being very difficult to actually not too bad. All right, then part B, which is a composite function style of question. We're given these two functions and we want to solve the equation hg of x is equal to 4, giving our answer in exact form. Well, what does hg of x mean? It means we're going to put the function g of x inside of h of x. So we're going to take this function here, g, and whenever we've got an x in here, we're going to put the function inside there. So what we're going to get is 3 big bracket ln 2x squared plus 5 minus 2. And what we're told is that that's equal to 4. So we can say that 4 is equal to 3 ln 2x squared plus 5 minus 2. We're going to add 2 to both sides. So we get 6 is equal to 3 ln 2x squared plus 5. I'm going to divide both sides by 3. So ln 2x squared plus 5 is equal to 2. Then we can convert this to exponential form. So our base is e, our power is 2. So we're going to get 2x squared plus 5 is equal to e to the power of 2. We can subtract 5 and divide by 2. So we get x squared is equal to e squared minus 5 upon 2. And then we're going to square root this. So x will be equal to the square root of e to the power of 2 minus 5 upon 2. And with the square root, we've got this plus or minus issue. But let's just go and have a quick think. We're told in the question that the domain is x is greater than 0 for both functions. So actually, we can't have the negative here. We can only have the positive. All right, so I'm just going to get rid of that. So that should be our answer. And I'm just going to check that against the mark scheme, ensure that I'm all right. Let's go to that. Yep, square root of e squared minus 5 upon 2, or exact equivalent. Okay, here we are in question 9. We want to solve this equation, giving our answer correct to 1 decimal place. Now, the best way to do this type of question is basically with a substitution. We're going to say let u equal x to the power of 2/3, because if I do that, then I can change this equation to be 12u minus 5u to the power of negative 1 minus 11 is equal to 0. And u to the power of negative 1 is the same as 1 divided by u, so I could sort of write it like that if I wished. And then I'm going to multiply everything through by u. So I get 12u squared minus 5 minus 11u is equal to 0. And 12u squared minus 11u minus 5 is kind of the more conventional way of writing that. That is a quadratic, and hopefully that quadratic is going to factorize in some way. We know that the two numbers here are going to multiply together to give negative 5. So we pretty much guarantee that one of these is going to be 1 and 5. Harder ways to know, but I think that's going to be 3u and 4u is my guess. And if I write negative 5 there and positive 1 there, I think everything will work out, because 3u times by negative 5 is negative 15u. 1 times by 4u is positive 4, and negative 15u plus 4u is negative 11u. Now that gives us two solutions. U is equal to negative 1/3, and u is equal to 5.4. And remember, we are solving not for u, but for x. So x to the power of 2/3 is equal to negative 1/3. And x to the power of 2/3 is equal to 5.4. Well, if we just take the first one, right? If I was to cube both sides, I would get x squared is equal to minus 1 upon 27. But then I can't square root both sides because I can't square root a negative number. So this guy's got no solution, or no real solution if we want to be more precise. This side, if I was to cube both sides, I would get x squared, beg your pardon, x squared is equal to 5 upon 4 cubed, which is 125 upon 64. And then if I was to square root both sides, well, I've got the square root of 125 over the square root of 64. Square root of 64 is 8. And 125 is 25 times by 5. So this is going to be 5 root 5 upon 8. Now, it asked me to do it to a decimal place, right? So I'm going to do 5 root 5 on my calculator, divide by 8. Get the decimal number, which is 1.3975, and it wants me to give it to correct to 1 decimal place. So I've got x is equal to 1.4, and I think I'll just quickly check the answer against the mark scheme, just make sure that I am correct. 1.4, yep, 1.4 only is our answer. Okay, so here we are in question 10, which is a circular measure question. The diagram shows a badge which consists of a minus sector OAB, that's that thing there, and a kite OBCD. So this thing is a kite, right? That shape there. And a kite is made up of two triangles like that. And these two triangles are right angle triangles, right? So if the angle B there is a right angle, that means that this guy here, D, is also a right angle. So that's probably worth indicating on there. The arc AB has length of 27, that's 27. And the line OB is perpendicular to CB, so that's that. Okay, so we want to find the perimeter of the badge. Well, if we want to find the perimeter, we need to know that length. We already know that length. We already know that length. We know this length, right? Because it's the same as this length here. And that length there is the radius 12. And this length here, DC, is going to be the same as this length here. So in effect, the question for the perimeter is going to boil down to whether or not we can find that length. And finding that length will be dependent upon whether or not we know this angle here, right? Because then we could use trigonometry. And how could we find that angle there? Well, I suggest what we could do is we could find that angle there, which I will call theta, right? So I'm going to call that angle theta. I'm going to call that angle there phi. And if we can find out both those angles, then we should be able to calculate the perimeter. So the formula for the arc length is S is equal to r theta. Our arc length is 27 and our radius is 12. So theta is going to be equal to 27 divided by 12, which is going to be 9 upon 4. Okay. Now, if theta is 9 upon 4, then phi is going to be pi minus 9 upon 4. And the reason for that is that this is a straight line, right? Then if we know phi, we can calculate that length because we can use trigonometry. So we can say that the length CB, right, which is this length here, can be found out in this way. We can say that tan phi will be equal to opposite CB over adjacent, which is 12. And therefore, CB is going to be equal to 12 tan phi. Well, okay, then now we just got to piece everything together, right? The perimeter, P, is going to be equal to the length CB, so that's 12 tan phi, so this length here, plus the arc length, which is 27, so plus 27, plus this length here, 12, plus that length there, 12, so plus 12 plus 12, and then plus another length like this, which is the same as 12 tan phi. So plus 12 tan phi. So if we put all this together, we've got 27 plus 24, which is going to be 51, and plus 24 tan phi. And phi was pi minus 9 upon 4. So then the last job for me is just to put this all into the calculator. And you need to first make sure your calculator is set to radians. So I'm going to do 9 divided by 4. I'm going to do pi minus that. I'm going to find the tan of that angle. And I'm going to times it by 24. And I'm going to add 51 to it. And the answer I get there is 80.7. That's going to be 80.7. Is it centimeters? Yes, centimeters. Okay, so that should be our answer. Okay, then part B, we want to find the area of the badge. And how are we going to find the area? Well, we've got to find the area of the sector. That's the first thing. And then the area of this kite. Well, the area of the kite is the same thing as finding the area of two of these triangles, right? So take the area of the triangle and double it. And how are we going to find the area of the triangle? Well, we can do a half the base times by the height. So why don't we just focus on doing that? So the area of the sector is going to be a half r squared theta. That's the formula. So let's just go down here. So area of the sector is equal to a half r squared theta. And our radius was 12, so it's a half 12 squared times by 9 upon 4, which was the angle of the sector. And I think it's probably a good idea we just key that straight into the calculator now. So 12 squared and times by 9, and then divided by 4 and divided by 2. Okay, 162. 162 is the area of the sector. Then what we're going to do is we're going to find the area of the triangle. Area of the triangle. Okay, and how do we do that? Well, we've got to do a half of this length here, CB, times by that height there. Well, CB is 12 tan phi, so we've got to times it by 12 and then divide by 2 to get the area of a triangle. So we could say that this is equal to a half times by 12 squared tan phi. But of course, we need two triangles, don't we? So we need to double that. We can say that the total area is going to equal to 162, which is the area of the sector, plus 2 lots of a half times by 12 squared times by tan phi. Right? And of course, the 2 and the half, they cancel off. So we've got 144 tan phi there. And if we remember, the phi was the same thing as pi minus 9 upon 4. So really now all I've got to do is just got to put that into the calculator. So 9 divided by 4, and then pi minus that. I'm going to find the tangent of that angle. I'm going to times it by 144, and I'm going to add it to 162, and I get 340.36. So 340, and I think 3 significant figures is going to be sufficient accuracy. Let me just double check that. Yeah, 340 or equivalent. So that answer is perfectly acceptable. Okay, so here we are in question 11. This is a vectors question. The triangle OAB, OA is the vector A, OB is the vector B. The midpoint of OB is this point X. The midpoint of AB is Y. And the lines OY and AX intersect here at the point Z. And it's given that AZ is lambda AX and OZ is mu OY. Okay, now I think it's probably best if we deal with all of these parts together. Because what we're asked to do in part A and B is to find two different vectors for OZ. Well, the way we're going to get those two different vectors is we're going to follow two different lines. So let me try to explain that. We're told in the question that AZ is equal to lambda AX. Okay, so that's that line there. Okay, and we're also told that OZ is equal to mu OY. So that's that line there. Now, hopefully what you'll notice is that the point Z is the intersection of those two lines. So really what we're going to try to do is we're going to try to define the vector that goes from O to Z in terms of the blue line and also in terms of the green line. Okay, so if we define it in terms of the green line, how can we go from O to Z? Well, we can go from O to A and then from A to Z. Right, so let's write that down. The vector OZ is the same thing as going from O to A and then going from A to Z. But the thing is, we know that A to Z is the same as lambda A to X because we're told that in the question. We can write like that. So now what we need to do is we need to find the vector AX. Well, what's the vector AX? We can go from A to O, like that, and then O to X. Well, the vector A to O is minus A, right, because we're going in the opposite direction, and O to X is a half of B. So we can write that down. We can say that OA is the vector A, and AX is minus A plus a half of B. Okay, and if I were to write that down, I would get 1 minus lambda in the A direction plus a half lambda in the B direction, right? So that's the first part. Second part, we want to define the same vector OZ, but this time in terms of the blue line, right? So we're going to go in that direction there. So we can say that OZ could also be defined as mu times by the vector OY, right? Because that's that blue thing here, like that. So mu OY. Well, then we've got to find out what the vector OY is. Well, how are we going to find the vector OY? Well, we could go from O to A and then A to Y. Okay, but we also know that A to Y is half of this vector A to B. So we're going to say OY is the vector O to A plus A to Y. And that's the same thing as O to A plus a half of A to B. So then we've got to think, what is the vector AB? And the vector AB is the same thing as OB minus OA. Minus OA, like that. Okay, if you're not sure about that, the vector AB, I do minus A takes me to there, and plus B takes me to there. Okay, so now I can simplify all this, hopefully, because what I've got is mu times by A plus a half B minus a half A. And so if I simplify all of that, I end up with a half mu A plus a half mu B. Okay, and that's another way that I can write OZ, this time in terms of mu, right? So I've already done part A and part B because I've got a vector in terms of lambda. I've got a vector in terms of mu. So now what I want to do is I want to find lambda and mu. Well, how can I do that? Well, what I'm saying is my two vectors are the same, right? This guy here is the same as this guy here, right? Because they're two identical vectors because they take me from O to Z. So what I can do is I can compare the components. I can compare the A's and I can compare the B's. Well, if I compare the A's, I know that 1 minus lambda must be the same as a half mu. So I can write that. 1 minus lambda is equal to a half mu. And if I was to compare the B's, then I can say that a half lambda, which is this thing, must be the same as a half mu. I can write a half lambda is equal to a half mu. And if that's the case, isn't it, then lambda is the same as mu. So what I can do is I can now substitute that into this equation. I'll call it equation 1. I get 1 minus lambda is equal to a half lambda. And rearranging that, 1 is equal to 3 upon 2 lambda. And therefore lambda is going to be equal to 2/3, which is also the same thing as mu. Right? So lambda and mu are equal to 2/3. Well, then part D is we want to find the vector OZ in terms of A and B. Well, we can use either of our two vectors here. It's best to use this one, I think. So it's a half mu A plus a half mu B. We can say OZ is equal to a half mu A plus a half mu B. And mu is equal to 2/3. So a half times by 2/3 is a third. So we get a third A. And the same thing here, a third B. Right, so OZ is a third A plus a third B. And what I'm going to do is I'm just going to double check that against the mark scheme. Make sure I got that right. Let's just go down. Yeah, exactly right. Okay, question 12. A curve has got this equation here. Part A is explain why the curve does not exist when x is less than 2/5. Well, essentially, the reason is we've got a square root here, and the number inside the square root cannot be negative. So that's the first thing we should really state. The number inside square root cannot be negative, or must be positive, right? So square root cannot be negative. So therefore, we could say something like 5x minus 2 must be greater than or equal to 0, which is the same thing as saying that x needs to be greater than or equal to 2/5, which is the same thing as saying x cannot be less than 2/5. So it cannot be less than 2/5. Okay, so something like that, some kind of reason. But essentially the idea, and I think what it says on the mark scheme, is this thing here, the number inside the square root cannot be negative. Okay, part B. Basically what we've got to do is we've got to differentiate the curve. And we've got to show that it can be rewritten in this form. Well, in this question, we've got one function divided by another function. So when we've got one function divided by another function, or the quotient of two functions, we need to use the quotient rule. We're going to call the function on the numerator u, so that's 5x minus 2 to the power of a half, because the power of a half is the square root, and we're going to call v x minus 3. And then what we've got to do is we've got to differentiate both of these. So we've got u prime. So if we differentiate that bracket, the half comes down to the front, and we reduce the power by 1, so that becomes a half to the power of a negative a half. And then what we do is we differentiate inside the bracket. So we differentiate 5x minus 2, we get 5, and we multiply through by the 5. For v, if we differentiate v, x differentiates to give 1, and negative 3 differentiates to give 0. Well, then what we need to do now is we need to remember what the quotient rule is. The quotient rule is v du minus u dv all over v squared. And the biggest mistake is usually that you get these the wrong way round. You get u dv minus v du. And that's usually because you're mistaking it with the product rule. And a lot of people remember the product rule as basically in the reverse order, u dv plus v du. So a way of avoiding that mistake, by the way, is I think memorize the product rule in this order as well, right? So memorize the product rule as vu prime minus, vu prime plus uv prime. Because if you memorize the product rule in that order, you're not going to make a mistake with the quotient rule by forgetting to switch the order. Okay, so I think that can be a helpful thing. All right, then, what we're going to do is we're going to substitute the values in. So v is x minus 3, u prime is 5 upon 2, bracket 5x minus 2 to the power of minus a half, minus u, which is 5x minus 2 to the power of a half times by dv, which is 1. And then all of this is divided through by v squared, and v squared is going to be x minus 3 all squared. Now, when we've got an expression like this, the major issue is getting rid of this term here, the term which has got a power of a negative. And how can we do that? Well, basically, we multiply through by the equivalent expression, but with the positive power. So in this case, I'm going to take the entire numerator, and I'm going to multiply it by 5x minus 2 to the power of positive a half, right? So this is 5x minus 2 to the power of negative a half. So if I want to get rid of this term, if I want to cancel it out, I need to multiply it by 5x minus 2 to the power of positive a half. But remember, I can't just multiply this term in isolation. I need to multiply the entire numerator. And therefore, if I multiply the entire numerator, I've also got to remember that I need to multiply the denominator as well, right? Because we need to have equivalent fractions. Okay, then, so if I'm going to now multiply all this out, this term here, if I multiply 5x minus 2 to the power of negative half by 5x minus 2 to the power of positive a half, what I do is I add the powers, I get negative a half plus a half, which is 0, and anything to the power of 0 is 1, which means that this cancels off. So what I'm left with is x minus 3 times by 5 upon 2. And if you want to write it, times by 1, if you prefer. The next term, this guy here, 5x minus 2 to the power of half, again, same thing. I add the powers, and a half plus a half is 1. So this guy becomes 5x minus 2 to the power of 1. And then on the denominator, what I would have is x minus 3 all squared times by 5x minus 2 to the power of a half. Now, I'd probably also choose to get rid of this fraction here, right? I don't like that, so I'm going to multiply top and bottom also by 2, just to get rid of that. So there you go, multiply by 2, and multiply by 2 on the bottom as well. And so therefore, if I do that, what I'm going to get is 5 bracket x minus 3 minus 2 bracket 5x minus 2, right? Because I've got to multiply the other term by 2 as well. On the denominator here, I'm going to get, how do they write it? They write it as the square root. Yeah. I'm going to get 2 bracket x minus 3 to the power of 2, 5x minus 2 to the power of a half, which is the same thing as the square root of 5x minus 2. Well, we're almost there now. So what's the last step? Well, we just got to simplify the numerator. Here I've got 5x, and 5x minus 10x, that's that term, is going to be negative 5x. And then what I've got here is 5 times by negative 3, which is negative 15. Then negative 15, and then we've got minus 2 times by minus 2, which is positive 4. So minus 15 plus 4 is minus 11. All divided through by 2 times by x minus 3 all squared, the square root of 5x minus 2. So I think that's going to be our answer there because we've simplified it. So if we were going to just factorize, I think, because it wants us to factorize the numerator, negative bracket 5x plus 11, all divided through by 2 bracket x minus 3 squared, square root of 5x minus 2, just to get it in the exact form that they want, which means that our A will be 5 and our B will be 11. Okay, I'm just going to double check that answer against the mark scheme. Yep, 5 and 11 is the correct answer.